Hello everyone. Today we will start with the module number 4, that is behavioral modeling. In the previous module, that is in the module number 3, we have discussed about structural modeling or gate level modeling and data flow modeling. So this is the third type of modeling, that is behavioral modeling. So in this gate level modeling, we used a circuit diagram or gate level description to design a module, whereas in the data flow modeling we used the boolean expression or how the data flow between the registers to describe a Verilog HDL module. So here this one is the third type of modeling, that is behavioral modeling. Here, as the complexity increases the circuit of the circuit, that is digital circuit, with the increasing complexity, it is become very important to make a design decisions early in the project. So whatever the application that you take to develop, so you need to take some design decisions very early, that is during the initiation of itself of the application. So here designers are going to able to evaluate the trade-off of various architecture and algorithms before they are going to design an optimum architecture and algorithm to implement that particular in hardware. Therefore, architectural evaluation takes place at an algorithm level here. So remember here, in the behavioral modeling, the architecture evaluation takes place in an algorithm level, where the designers do not actually need to think in terms of a logic gates or data flow. Whatever we have done in the previous cases, that is we used a logic gates as well as we used data flow between the registers. Here the designers need not to think in that view to design the model, but they are going to think in terms of the algorithm, whatever they want to wish to implement in hardware. So the basic building block of the behavioral modeling is nothing but an algorithm. That means they are more concerned about the behavior of the algorithm and its performance. So they do not want how the circuit looks like, how the data flows in between the registers, but they are concerned about the behavior of the algorithm and its performance. So only after the high level architecture and algorithm are finalized, then only the designer starts focusing on building the digital circuit to implement the algorithm. So therefore Verilog HDL or Verilog provides the designers the ability to describe design functionality in an algorithm manner. The meaning of this one is the designers describes the behavior of the circuit. So designers describes here how the circuit behaves, that is the behavior of the circuit. That's why the name is behavioral modeling. Therefore behavioral modeling represents the circuit at very high level of abstraction. So as we have discussed in the module number 1, what is the level of abstraction? So behavior modeling has the highest level of abstraction for this reason. So the design at this level is almost similar to the C programming, more than it resembles the digital circuit design. So it is almost similar to the C programming language instead of the digital circuit design. When you study the complete behavioral modeling, you will come to know how many so many C programming constructs are used in the behavioral modeling. That's why behavioral Verilog constructs are similar to the C programming language constructs in many ways. So Verilog is a very rich in behavioral constructs, and that is going to provide the designer with a great amount of flexibility. So this is the introduction of the behavioral modeling. So let's discuss the behavioral modeling in detail. So first topic in the behavioral modeling is structured procedures. So there are two structured procedure statements in a Verilog. The first one is always and the second one is the initial. There are two structured procedure statements in Verilog. So those are namely initial and always. So initial and always, both these are the keywords in behavioral modeling. So these statements are the two most basic statement in a behavioral modeling. Without these statement, you cannot write behavioral modeling program itself. So all the other behavioral statements can appear only inside the structured procedure statements. Then that means whatever the any other statements that you are going to write, either you are going to use the initial statement or always statement. Within that only all the other constructs are written. So Verilog is a concurrent programming language. Remember here, Verilog is a concurrent programming language, whereas C programming is a sequential programming language. Sequential means the statements are executed one after the other, whereas concurrent means at a time more than one statements are initiated and starts executing. That means you can say the parallel execution of statements are possible. That is nothing but a concurrent programming language. Verilog is a concurrent programming language. So how exactly the concurrent means, that is going to be discussed here in this modeling. Activity flow in a Verilog run in parallel rather than in sequence. That is nothing but a concurrent, the behavior of the concurrent statements. That means activity flow in a Verilog run in a parallel. Multiple statements are going to run at the same time. Unlike in C programming, the statements are executed one after the other, that is sequential in nature. So each always and initial statements represent a separate activity flow in Verilog. So whatever the statements that you are writing in a always block or initial block, that represents separate activity flow in a Verilog. Each activity flow starts at a simulation time 0. By default, the simulation time of starting of the each activity is going to be a 0. The statement always and initial cannot be nested. So what do you mean by nesting? That is initial within initial, that is not possible. So statements always as well as initial both cannot be nested. First, let us discuss what is initial statement. So initial is a keyword here. So all the statements inside the initial statement constitute an initial block. So whatever that logic or the statements that you are going to write within a initial keyword, those are called as initial block. So the initial statement constitute an initial block. So an initial block starts at time 0. Remember here, all the initial block are starting at the time 0 by default and executes exactly once during a simulation and then does not execute again. So remember this one, very important. In a, whatever the statement that are written in an initial block, they are going to execute exactly once. They are not going to repeat again. They execute only one time. So if there are multiple initial blocks, each block starts to execute concurrently at a time 0. So you can have more than one initial block. Say you have 4 initial blocks in your module. So all the 4 initial blocks are going to start executing exactly at the time 0. That's why it is called as a concurrent execution. So each block finishes execution independently of other blocks. Here all the initial blocks starts execution at the same time, but it does not mean that they have to end also at the same time. Every initial block going to end its execution independently of the other blocks. Remember here, because one initial block may contain only one statement, other initial block may contain more than one statement, two statements, three statements, four statements, or any number of statements. So in that's why all the initial statements are going to start executing at the same time, that is 0, but they are not going to finish the execution of that particular initial block at the same time. They are going to finish independently of the other initial blocks. So multiple behavioral statements must be grouped, typically using the keyword begin and end. So you might have studied in C programming the grouping of the statement. If you have only one statement, there is no need of grouping. But if you have more than one statement, multiple statements within an initial block, that can be grouped. Grouping means they belong to that particular initial block only. They can be grouped by using begin keyword and end keyword. In C programming, that is done with the curly brackets. Open curly brackets, write all the statements, then close the curly bracket. That is nothing but a grouping in C programming. Here grouping is done by using the begin and end keywords. So here, if there is only one behavioral statement, of grouping is not necessary. Then if this is similar to the begin end block in Pascal programming language or the C programming language also, the curly brackets grouping in the C programming language. So there are some examples here. Initial statement. Here the module stimulus, you have a register variables reg x comma y comma a comma b comma m. See here now, initial is a keyword. So within that, whatever is written, that is called as the initial block. So m is equal to 1 tick b 0 is the initial block here. It consists of this initial statement consists of a single statement. That's why it does not need any grouping, because it is having only one statement. So this is the end of the first initial block. You can have more than one initial block in your program. So see here, second initial block, again initial. So as we have more than one statement, that is multiple statements are available here, that must be grouped. That's why a begin keyword is used. So begin followed by two statements, then end of that initial block. So this initial block has two statements. So #5 is nothing but it is a delay. That means this initial block starts execution exactly at 0 time unit, but as the delay is provided here, the time after elapsing of 5 time units, this statement a is equal to 1 tick b1 is executed. Then here, as these statements are concurrent statements, so the #25, that means after the completion of the 5 time units, then this statement is going to start executing. That means it ends at 30 time units, that is 25 plus 5. So total time unit required to execute the last statement. First it begins at 5 time units, then it ends after 25 time minutes. So 25 plus 5, so 30 time minutes it is going to end. So third initial block, again there are multiple statements. So begin #10 is a delay time, then x equal to 1 tick b0, 1 tick binary 0, and #25 y equal to 1 tick b1. So again here there are two statements, that's why begin and end it is grouped. So observe there are total 4 initial blocks here. In the last initial block we have #50, then system task $finish is there. That means it is end of the simulation. So all the 4 initial blocks start concurrently at the time 0, but they are not going to finish at the same time. They are independent of each other. So the first initial block is going to finish exactly at the time 0 itself, because there is no delay here. In the second initial block is going to finish at 30th time unit. Third one 10 plus 25, so total is 35. So it starts at 0 but ends at 35 time units. And the last one, system task finish, is going to execute after 50 time units. It starts at 0 and ends at 50 time units. So in this example, the three initial statements starts to execute in parallel at time 0. If a delay hash followed by the number delay is seen before the statement is executed after the delay time units after the current simulation time. Therefore, the execution sequence of the statement inside the initial block will be as follows. See here, the execution time is given here. First statement starts at 0 and the statement executed is m is equal to 1 tick binary 0. So in the second initial block we have a 5 time units. So after 5 time units, a is equal to 1 tick b1 is executed. Then observe here, the next statement that is executed is going to be the x, because it executes after 10 time units, because all the initial statements starts executing exactly at the 0 time unit. So this statement also execute after the specified delay time. So specified delay is 10 time units. That's why x equal to 1 tick binary 0 is executed after 10 time units. Then the b is equal to 1 tick binary 0 is executed. So b is executed after 25 time units, but before that there is a statement. A statement is executed after 5 time units. That's why b is going to start after completion of the a statement. That's why the time units taken to complete the execution of b is 30 time units. Similarly, in the next initial block we have a y equal to 1 tick b1. So original delay of that one is 25, but before that x is executed because it starts at time 0. So after 10 time units it is executing. So after 10 time units this statement is going to start executing this block. That's why, so total time units taken by this y is equal to 35 time units. And the last one is $ finish, that is system task it is. So it has only one statement in that initial block. That's why it starts executing at time 0, but it completes the execution after 50 time units, because 50 time units is the delay provided in that statement. So the initial blocks are typically used for initialization, monitoring and waveforms and other processes that must be executed only once during the entire simulation run. So as we have already told you, in whatever the statements that are written in an initial block, they are going to execute only once. That's why they are going to be used for initialization purpose. Initialization is only done once. Then monitoring is done continuously, and for the waveform and some other processes also it is used, and they are going to be executed only once during the entire simulation run. So the following subsection discussion how to initialize the values using alternate shorthand syntax. So whatever we have used until now, the same thing, the execution is going to be same, but the appearance is going to be different. You can have that initialization values in different ways. You can choose any one which is in which you are comfortable with. So the use of the shorthand syntax has the same effect as an initial block combined with a variable declaration. So see here, combined variable declaration and initialization. So the initial value assignment. So observe there, the clock variable is defined first here, that is reg clock. Then its value is going to be set as 0. Initial clock is equal to 0. So instead of using these two statements, the same can be done by this method. That is, instead of the above method, the clock variable can be initialized at the time of declaration itself. So this is allowed only for variables declared at the module level. So that is, instead of defining first then initializing the value, you can do it in a combined way, that is reg clock equal to 0. During the defining itself, the initial value of the clock is also declared. So example here, module adder, the list of the variables sum cout a comma b comma scene, output reg 7 down to 0, sum is equal to 0. See here, initial value of sum is equal to 0, that is sum is a 8-bit value, 7 down to 0. So all the 8 bits are initialized with the value 8-bit. So this is a output variable. Similarly, the C naught, that is it is also output, but it is a scalar one, single value. So 1-bit value is initialized for C naught, that is equal to 0. So initialize 1-bit output for the C naught. So this is how the combined port declaration and initialization is done. There is one more method, that is ANSI C style port declaration and initialization. So if you take the previous example itself, during the declaration itself, the initial value of that one is going to be done. So this style of initializing is called as ANSI C style. So see here in the module, so this one this type of initialization we have discussed in the previously in the module number 1 or 2. So module adder, so observe here in the bracket itself, in the previous case we have just listed the variables sum c naught a comma b comma scene, but here we have declaration as well as initialization is done here. So output reg 7 down to 0, sum equal to 0, and output reg c naught equal to 0. Whatever we have done it outside in the previous example, that is done during the listing itself. So this is called as ANSI C style. So until now we have discussed the initial statement. So this is one of the structured procedure. The second structured procedure statement in Verilog is always statement. So all the behavior statement inside an always statement constitute an always block, similar to the initial block. As when you write the initial statement consists of an initial block. Similar to that one, always statement constitute of a always block. So there are statements written within a always statement, so that those statements are called as always block. So the important thing for always block is the always statement start at time 0 and executes the statement in the always block continuously in a looping fashion. Here initial whatever we have discussed previously, the previous topic, it executes exactly once, but whereas the always statement, it is going to execute again and again. So that's why it is called as looping. Looping means in loops until some condition is satisfied, it again and again it is going to repeat. But here there is no condition here, it is going to be repeated continuously until if you specify or terminate it forcibly by using the interrupt or power of method. So this statement is used to model a block of activity that is repeated continuously in a digital circuit. Like for example, a clock pulse. If you initialize a clock pulse with value 0 and you want to complement that value to get a clock pulse value as 1, so this is a complete period. So such kind of clock pulse is required continuously for a longer period of time. That's why such statements are executed using always block. So as an example, a clock generator module that toggles the clock signal every half a cycle. So in real circuit, the clock generator is active from time 0 as long as the circuit is powered on. So here the example for the always block. So here clock generator is taken as an example. So module clock generator, output reg clock. So this is a declaration. Now initial whatever the statement that we have discussed earlier, that is initial, it is going to execute only once. So clock value is declared here. Its initial value is 1 tick binary 0. That means clock value is 0 now. Now toggle clock every half cycle. So the time period given is 20. So for a complete clock pulse, we have a time period is 20. So clock has a turn off time and turn on time. So total time is nothing but, or total period is equal to turn off time plus turn on time, that is equal to 20. So turn on time is 10 and turn off time is 10 here. That's why always in the always block #10, the delay time unit is 10. Clock is equal to not of clock, that is complement of the clock pulse. So clock is initialized with value 0. So when this statement is executed, its complement value is assigned to clock, that is clock equal to 1 after execution of this statement. But at what time? That is after 10 time units, because the off time is 10 and on time is 10, turn off time and turn on time. So total time period is 20. So after every 10 time units, this statement is executed, that is clock is equal to not of clock. So initially it is 0, then it becomes 1 after 10 time units. Again after 10 time units it becomes 0 and it becomes 1 after next 10 time units. Like this it go on repeatedly executes, because it is written under always statement. So always statement execute in a looping fashion without the end. If you want to end, you should end it forcibly. So to end this statement, the clock pulse, what is done? See here, again we have initialized the block initial #1000 time units. So after 1000 time units, the system task is used, that is $finish. So this is forcibly terminates the simulation. That's why the clock pulse executes from 0 time units up to 1000 time units continuously. Number of clock pulses are generated, but after 1000 time units, the forcibly we have stopping or terminating the program by using the system task $finish. End the program by using end module. So here in this example, the always statement starts at time 0 and executes the statement clock is equal to not of clock after every 10 time units. Notice that the initialization of a clock pulse has to be done inside a separate initial statement. Why this is done? Because initial statement, if you again take it in always block, again and again the initial value of clock is done here, that is 0. So we need not to do this one, that has to be done only once. That's why it is done within a initial block. Also the simulation must be halted inside an initial statement. If there is no stop or finish statement, to halt the simulation, the clock generator will run forever here. So this is just like a infinite loop in C programming. So in C programming we have an infinite loop. So if you do not have any forcible stopping, the infinite loop is going to be continuously executing. For example, while 1, so always true, while 1 is always true, so it executes again and again without the stop. So to stop that one, either we have to use a $stop or $finish. That is stop is nothing but it is an interrupt. It stops temporarily or suspended temporarily, whereas power off is nothing but it is termination of that particular block. So the hardware designers tend to view it as a continuously repeated activity in a digital circuit starting from power on. Thank you for watching the video.